All right, how's everyone doing today? That's good. I wanted to go get McDonald's or something this morning, but my car is buried under a foot of snow, so that didn't happen. So I hope your morning's going better than mine. Okay. Yeah, I think they have. I think they got like bacon, egg, and bacon, egg, and cheese biscuits, like 2 for $4 or something like that now, which really sounded good this morning, but alas. Hash browns? Don't know about that one. Don't know about that one. The hash browns are okay, but the bacon, egg, and cheese biscuit is primo. Alrighty. So I believe we left off yesterday. The last example we did was the equation of a plane containing 3 points, correct? On Monday. Put the hash brown on the biscuit. That's actually not a bad idea. Maybe. Okay. Cool. Why is this making so much noise, man? All right. So just a reminder. So oh my God. Okay. So just a reminder. So the equation of a plane. So we need 2 things. Every question asking you to find the equation of a plane, you want to find 2 things. What are those 2 things we want to find? What 2 things do we need for the equation of a plane? Right, so we need a point and we need a normal vector, correct? So the equation of a plane through point x naught, y naught, z naught with an orthogonal vector, which we always call the normal vector, usually call it n. So it's got a normal vector ABC, and it goes to the point x naught, y naught, z naught. So there's a vector equation too, but we don't use it that often. I don't believe this book uses it that often either. But the scalar equations, or the scalar equation is so a x minus x naught plus b y minus y naught plus c times z minus z naught equals 0. So that is probably if you have the point and you have the normal vector, that's the easiest equation to do, if that is an option for you. Or you can expand it out and put the constant on the other side. So just a reminder, so you have A, B, C are the components of your normal vector, and your x naught, y naught, and z naught, remember it's minus those, are the coordinates of your known point. Or you can expand it out and throw the constant on the other side. And it doesn't, you don't have to know this, but it is nice to know that that constant d is just the position vector for your known point dot the normal vector. That constant is just a dot product of those. And in fact, it doesn't matter what point you pick, x naught, y naught, z naught. So you can pick any point on the plane, and when you take the dot product of the position vector for that point and the normal vector, you get the same constant. In fact, that's what this is saying here. This is just the position vector for any point on the plane, x, y, z, dot the normal vector, a, b, c. So this equation is just saying you take the position vector for any point on your plane, you dot it with the normal vector, you're going to get the same constant, no matter what point you pick on the plane. Do x, y, and z represent the difference between x and x naught? Not quite sure I follow. So for the equation of your plane, so for this equation here, x, y, and z are just the coordinates of any point on your plane. So if you pick any point on your plane, x, y, z, and you plug in x, y, and z into the equation, it should satisfy this. Okay, gotcha. But you always want to find a point and a normal vector. Those two things are what you always need to find when you need to find the equation of a plane. Okay. So there are lots of different questions we could ask about planes, but one thing is we could look at the intersection of a line and a plane. So if you have a line which is not parallel to your plane, it's going to intersect the plane in a point. So let's consider a line and a plane and try to find the intersection of the two. Doesn't matter, just want to cover my bases. So find the point of intersection of the line which is given by the following equation. So there is a bit of confusion on some of the homework for some of this language. So when we write the equation of a line like this, we say we're parameterizing the line. So parameterizing a line just means you're turning it into a function of a single parameter t, right? A single variable t. So that's what we mean by parameterization of a line. And we'll get more into detail later on parameterizations, but that's what that means. So our line is 1, 2, 1, so written in vector form, plus t times negative 2, 0, 1. And the plane (3x) minus 9y plus 2z equals 7. Okay, so all right. So the way a point of intersection of two things is just a point which lies on both objects, right? A point which satisfies both equations. So what we want to do is we want to find a point on the line which also lies on the plane. And the way I like to think of points on lines when you parameterize them, when you give them, right, an equation involving t, is you can think of every point as being as corresponding to some value of t. Right, we'll see later that when you parameterize a line, you can think of it as describing a particle moving along your line in time, and your particle is at some point at a given time t, right? So when you plug in a value of t, that gives you a point on your line. Technically, a vector corresponds to that point, but same thing. So what we want to do is we want to find a value of t. We want to find the value of t where we hit the plane, basically. So the way we're going to do that is the following. So this is sort of the vector equation for that, but when we put it in like the scalar parametric form, this means the line consists of the points x, y, z, for which x is equal to, so we look at the first component of the vectors here. So if we combine it, the first component we get 1 plus, minus 2t. Right, we're just writing 1, 2, 1 plus t times negative 2, 0, 1 as a single vector. And then the first component is what x is equal to. So we get 1 minus 2t. What's the second component? Y is equal to what?
2.
Just 2. 2 plus 0 times t, which is 2. Whoops. And then the third component is z is equal to, so 1 plus 1 times t, so 1 plus t. So these are scalar parametric equations for our line. So the line consists of the points x, y, z, for which x is equal to 1 minus 2t, y is equal to 2, and z is equal to 1 plus 2t for some value of t. And we let t go from negative infinity to positive infinity. So those describe all the points x, y, z on our line. And this equation describes all the points x, y, z on the plane. So you want to find a point which lies on the line and the plane, some point x, y, z. And so we substitute this expression in for x, this expression in for y, and this expression in for z, right? Because it has to satisfy both equations at the same time. So we get 3 times 1 minus 2t, because for all points x, y, z on the line, x is equal to 1 minus 2t. minus 9 times 2, because y is equal to 2 on the line, plus 2 times z, or sorry, 1 plus t, because z is equal to 1 plus t. And then we solve for t, right? So just get t by itself. When we do that, so we get, so negative 6t plus 2t and then we get 3 minus 18, so negative 15 plus 2, negative 13. Bring it over, and we get 20. So t is equal to negative 5. So that's, if you think of moving along your line, at time negative 5, that's when our particle hits the plane. But that is not a point, right? So to get the point, we plug in that value of t into our equations to get the x, y, and z coordinates of the point. So when we do that, what point do we get? All right, we get to get 1 minus 2 times negative 5, so we get 11, and then 2, and then 1 minus 5 is negative 4. And that's our answer. Right, so we just figure out what x, y, and z are in terms of t. On the line, plug those values in for x, y, and z, make the substitution into the plane equation, and then solve for t. And then plug that value of t back into the equation of your line to get a point. Any questions about that example? Shouldn't x be negative 9? No, because it's 1 minus 2t. Yeah. If it were 1 plus 2t, it would be, but yeah. Okay. So we can also look at the equation of a plane containing, like, there are lots of different ways we could, things we could ask to describe a plane, and then you would have to find the equation. One of those is we could describe a plane containing 2 lines, right? Suppose it contains this line and this line. That's one such thing we could do. So here's sort of a more possibly confusing example of that. And let's see if we can figure this one out. So let's find the equation of the plane containing the 2 lines. L1 is the first line. That's going to be 2 plus t. Y is equal to 3 minus 2t. And then z is equal to negative t. And L2 is going to be the line given by the equations x is equal to 3 minus 2t. Y is equal to 3 plus 4t. Z is equal to 1 plus 2t. Okay, so let's see if we can figure out how we would do this. So let's suppose we have some plane containing a couple lines, so L1 and L2. As always, we need to find a point, and we need to find a normal vector. Okay, so how do we find a point? What would be a point in this?
Should we set the lines equal to each other by components?
You could, but that's more work than you need to do, right? Because that gives you, if the lines intersect, that gives you a specific point, which lies on both lines. But in fact, like you could just pick any line on either point, right? So you could just plug in some value of t into one of the equations. Also, I wanna be careful. Be careful. So these are like two separate equations. The t values are like not related to each other. So maybe it would have been better to call it like this one S rather. Let me do that. Let me do that. Okay. So you could just pick any point on either plane, right? Remember, a point is just you plug in a value of t, or in the case of the other guy, some value of s. That's a point. Just plug in t equals 0. You got a point. So when we do that, plug in t equals 0 into the first line, we get the point 230. You can plug in any value of t you want. You could use the other line. It doesn't matter. Just that's the easiest way to find a point. Okay, normal vector.
Is that for line 1?
Yes. So 230 corresponds to t equals 0 from line 1.
Okay, so do we need can we choose either, so if we need a point, can we choose either line? So, because we need a point and the normal vector. Okay, awesome.
Yeah, you can pick any point on either line and you're fine. Doesn't matter. So I could plug in t equals 5. I could plug in t equals a half. I could plug in s equals 0, s equals -3. It doesn't matter. Like they're all going to be a point. And just make it clear that like where you got it from, and you'll be fine on an exam. Yeah. So normal vector. So from this picture, how could we find a normal vector from these two lines? From the picture here.
The cross product of the two.
Cross product of what exactly from the two?
The two lines, like their components.
Right. So you have the right idea. I just wanted to make it obvious what we were talking about. So the first line, we have a parallel direction, V1. And the second line, we have a parallel direction, V2, which you can get directly from the equations of the lines. So those two are vectors which are parallel to your plane. We can take their cross product to get a normal vector in theory, right? So what is the normal vector from the first guy? Sorry, not normal vector. I'm sorry. What's the, so on the first line, what's the parallel direction? What's the parallel vector, right? So we have 1, -2, -1. And what's a parallel vector from the second direction? Right, so instead of, we call it S, but yes, correct. We call it S, but you can call your variable whatever you want. I just call it S so we don't get it mixed up with a T, but just in your mind, replace it with T. And we see that the direction of this line is -242. Okay, so we could calculate the cross product here. And in theory, we should get a normal vector. Without calculating anything, can you eyeball these two guys and tell me what's going to happen when I take the cross product? What is the relationship between V1 and V2? Right, exactly, Nate. That's what's going to happen. Notice V1 and V2 are scalar multiples of each other, right? V2 is -2 times V1. So that means these two guys are going to be parallel vectors. And remember, we said when we take the cross product of two parallel vectors, we get the zero vector. And the zero vector is not a valid normal vector for a plane, right? Because the zero vector is not perpendicular. It doesn't have a direction, right? If you plug this into your equation, you're going to get 0 equals something. And that's not going to be helpful. So this approach is not going to work here. Here's the situation now. We don't have two intersecting lines. We have two parallel lines. And we can't take the cross product of their direction vectors because we get the zero vector. So how can we get a normal vector to the plane? So what we want to do, anytime you want to get a normal vector, there's usually going to be a cross product involved, right? And so what we want to do is we want to get the cross product of two vectors parallel to our plane, which are not parallel to each other, right? Because then we'll get the zero vector. How do you get the zero vector? By taking the cross product? Well, you could take the cross product. If you calculate it out, you get the zero vector. But remember, it's a fact that if two vectors are parallel, when you take their cross product, you get the zero vector always. You can, that's a good thing to know. Can save you a little bit of time. Okay, so how do we get, so we have one vector, right? V1, vector from the first guy. How do we get a second vector from these two lines, which is not parallel to V1? What's something we could do? So we have two lines. How can we take those two lines and get a vector parallel to our plane, a vector which lies in the plane? No. So dot product is going to give us a scalar. So think about points on each line, right? We can find a point on line 1, just plug in some value of t equals 0. Midpoint, I think you're on the right track, but there's actually something even simpler, right? So just pick any point on the first line, just plug in t equals 0. Pick any point on the second line, plug in s equals 0. And look at the vector from that first point to the second point. Notice that is not going to be parallel to either of these lines, but it's going to be parallel to the plane, right? It's a vector from some point in the plane to another point in the plane is always going to be parallel to your plane. And so we're going to find that vector, and then we're going to take the cross product. So, right. So let's just plug in t equals 0. We get the point. 2, 3, 0. Plug in s equals 0 into the second point. We get the point 3, 3, 1. And we look at the vector from P to Q. So P to Q is just 1, 3 minus 3 is 0, and 1 minus 0 is 1. So we have the vector 1, 0, 1, which is parallel to our plane. It's from one point in the plane to another point in the plane, always going to be parallel to our plane. And that is not parallel to the vector 1, negative 2, negative 1, which we know is parallel to our plane because it's the direction vector for our line. So let the normal vector be the cross product of that B1, which we said was 1, negative 2, negative 1. And this PQ, which is 1, 0, 1. And we'll get something which is non-zero, thankfully. When we take the cross product, let me do this real quick. We get negative 2, negative 1 minus 1, negative 2, 2.
Can we use either when like for example, you use the 1, negative 2, 1 here. Could we have also used the negative 2, 4, 2?
Yeah.
Oh, okay.
Exactly. And in fact, you don't have to use PQ here. You can pick any point on line 1 and any point on line 2. But that's, yeah, totally fine. Totally fine. You just need some vector parallel to your plane and some other vector parallel to your plane. But you don't want those two guys to be parallel to each other. Otherwise, when you take the cross product, you get the 0 vector. But any two such vectors will be fine. So when we take the cross product, we get negative 2, negative 2, 2. So the equation of our plane, if we just plug this directly in, we said, remember, our point was 2, 3, 0. So plugging this all in, we get negative 2, x minus 2, minus 2, y minus 3, plus 2, z minus 0, or just z, equals 0. That's a perfectly acceptable answer. One thing I want to point out, like I mentioned, so remember there are infinitely many equations for your plane, right? Because you can just pick any point you want and you'll get a different equation. And you can pick any scalar multiple of the normal vector, and you're going to get another vector which is also orthogonal to your plane. Sure. So when we took the cross product, it just so happened, because of the vectors we chose, that we got the normal vector was negative 2, negative 2, 2, right? But you could take some other cross product, you get a different thing. And if this were like multiple choice, the equation might not look exactly like that, right? So in fact, another perfectly valid normal vector, we could just multiply this by like -1/2, would be 1, 1, -1, right? I guess that's a quote unquote simpler normal vector, which works. And then you could plug that into your equation. And we got the 0.230 on there. So, whoops, sorry. So we could get x1 times x minus 2 plus 1 times y minus 3 minus 1 times z minus 0, so minus z equals 0 is also another possible way to express the equation. Does everyone understand that point? So I happen to pick this 0.230. I could have picked any point I wanted. When I took the cross product the way I did it, I happened to get -2, -2, 2. But I could have picked any other point, and I could have done some other cross product, and I would have ended up possibly with a scalar multiple of -2, -2, 2. So it's good to be able to look at an equation and recognize that that is still an equation for this plane. Right? The 1, 1, -1 is still parallel to our normal vector, which is still a normal vector. And we see the 0.230 is still on there. Does that make sense? Okay. Okay. So let's talk briefly about the angle between two planes. So if I have two planes, I'm not going to attempt to draw this here. But the way we find the angle between the two planes is we look at the angle between the normal vectors. If the angles between zero and pi over 2. Let me see if I can. Oh my goodness. Okay, so let's look at it. Pretend we're looking at the angles like here. This will work better. Pretend we're looking at the planes from the side, right? We'll consider these two lines. This will illustrate the point, right? So if you want to talk about the angle between the two lines, there are actually two options you could pick, right? We could pick this guy, or we could pick this bigger angle, right? One of the two is always going to lie between 0 and pi over 2. And the other is always going to be between pi over 2 and pi, right? Because the two angles have to add up to pi. One of them is going to be bigger than pi over 2. One of them is going to be smaller than pi over 2. So the way we're going to measure the angle between planes is we're going to take the smaller of those two, right? So pretend you're looking at the planes from the side. We're going to take the angle which lies between 0 and pi over 2. But the problem is the normal vector, the two normal vectors could have an angle bigger than pi over 2, right? So suppose we look at the normal vectors and the angle between them is bigger than pi over 2. Well, what do we do in that case? Well, suppose this is normal vector from the first, that's normal vector from the second. So basically what you want to do is instead of considering if the angle is bigger than pi over 2, instead of considering the two normal vectors, make one of them negative, right? It'll point in the opposite direction. Now we get an angle which is in fact less than pi over 2. And what we're doing is we're just changing the sign of the dot product. Well, let's do an example here to illustrate this. So we have a plane x minus c equals 8 and a plane y plus c equals 3. Okay, so the angle is the angle between the normal vectors. So what's a normal vector on our first plane? It's going to be 1, 0, negative 1. And the normal vector on our second is going to be 0, 1, 1. Right. So we're going to find the angle between these two normal vectors. Well, you should have this memorized. Remember, the angle between two vectors is related to the dot product in the following way. So we know cosine of the angle between the two is the dot product of the two vectors divided by their magnitudes. How did you get those normal vectors? So we can rewrite the equations in slightly. So x minus z equals 8, you could write as x plus 0 y minus z equals 8. So 1 times x plus 0 times y plus 1 times z equals 8. Or sorry, minus 1 times z equals 8. So the coefficients of x, y, and z give you the components of the normal vector. And so we get 1, 0, negative 1. Yeah. Okay. So when we take the dot product, 1, 0, negative 1 dot 0, 1, 1, we get, of course, 0 plus 0 minus 1, negative 1. And what's the magnitude of in 1?
Square root of 2.
Right, so we get square root of 2 for magnitude of n1, and the magnitude of n2 is also square root of 2. So we get negative 1/2. Okay, so remember, if your dot product is negative, then the angle between your two vectors is obtuse, right? If your dot product is positive, the angle between your two vectors is acute, which is what we want, right? We want the acute angle between here, the angle between 0 and pi over 2. But we got two vectors where the angle between them is bigger than pi over 2. It's obtuse because the dot product is negative. So in fact, when you want to find the angle between planes, really just take the absolute value of the dot product. And the reason for that is what we talked about here, right? So if N1 and N2, the angle's obtuse, if you, instead of considering N1, you consider negative N1, right? Now the angle is acute. That's what we want. And when you take the dot product of negative N1 and N2, you're getting negative the original dot product. And if you got something negative, you're just taking the absolute value there. Does that bit make sense? So when you're finding the angle between planes, you need to remember that cosine theta is the dot product divided by the magnitudes. But instead of the dot product, we want the absolute value of the dot product. For this reason, because we could get a negative dot product. And that would give us an angle bigger than pi over 2. But if we take the absolute value, then that's going to give us the acute angle corresponding to that guy. Why can't, it's just the way we define the angle between planes, right? So if we have two lines, like you have two choices, you could say this is the angle between them or this is the angle between them. And we just choose the smaller to be the angle. Yeah, it's just a convention. Okay, so when we do that, we get cosine theta is 1/2. So theta, that's a nice round number. What do we get for theta? Oh, no. So in this, just get used to doing radians. You're not wrong, but get used to using radians, right? Let's say pi over 3. So remove degrees from your brain and get used to thinking in terms of radians. And of course, we would have been okay doing it the other way. So we would have done this when we got cosine theta is negative 1/2. And then we'd say, okay, so that means theta is 2 pi over 3. That's the angle between those two guys. That's not what we want. We, in fact, want pi minus 2 pi over 3, which would be pi over 3, because we recognize that that is bigger than pi over 2. And so we want the complementary guy, right? Or I guess a supplementary guy, pi minus that. But if you don't have a nice number, so if we had like cosine theta is like 1/√6 or something like that, then you would just have to say the angle is cosine inverse of that. And yeah, I mean, I would just remember the formula, right? So when you're finding the angle between planes, take the absolute value of the dot product. Right, so if our dot product was like negative 1/√6, or like when we did all this, we got negative 1/√6. Well, you take the absolute value, you get 1/√6. So the angle would be cosine inverse 1/√6. Sorry, I hope that was not too confusing. I kind of went around in not the most direct manner there, but yeah. And one last thing I want to mention really quickly is it's going to be useful, especially later, to be able to sketch planes. And the way we're going to do that is we're going to find the intersection of the planes with the coordinate axes. Find the intersection with the axes in R3. And then connect them. And then that's going to give us the piece of the plane which lies in the first quadrant. Right? So suppose our plane intersects the x-axis here, the z-axis here, the y-axis here. Connect those guys. That's a sketch of the plane, right? We get the piece of the plane. In the first octant, sorry, octant, not quadrant, where x, y, and z are all positive. And so if we know how to find the intersection of a plane with the axes, then we can do this very easily. So let me look at it, do a very, very quick example. Love it. So let's sketch 3x plus 2y plus z equals 6 using that method. Okay. So the coordinate axes, points on the x-axis, right? So points on the x-axis, 1, 0, 0 is on the x-axis, 2, 0, 0, etc. On the x-axis, y and z are both 0 for all points on the x-axis. So we want to find, we're going to have a point, what 0, 0 lies on this plane. So you plug in 0 for y, 0 for z. So let's look at the x-intercept. Set y and z equal to 0, solve for x. When we do that, we get x is equal to what? So 3x plus 0 equals 6. X is equal to 2. So we get 2, 0, 0 is our x-intercept. Similarly, for the y-intercept, set x and z equal to 0. Doing the same thing, we get 0 plus 2y plus z equals, or 0 equals 6, y equals 3. So we get 0, 3, 0. And then z-intercept is 6, 0, 0, 6. So connect those guys. That's a piece of our plane lying in the first octant. And we can ask several things about this, but that's how you would sketch these. As long as you know how to sketch these, you should be able to work out those problems. Any questions about anything today? Alrighty. So tomorrow we're going to go over 12.6. It's not going to take 2 days. Really, I'm going to teach you like sort of the overall thing, how to find what we'll call traces of these surfaces. And then essentially you're going to want to memorize. So if you know how to sketch those traces and you memorize what the formulas look like, that's going to be all you need to know from the next chapter. So we'll go over that tomorrow, and I will see you guys later. Have a good one.
Professor, with this quiz on Friday, will you just like post it on Canvas and then we'll have to at some point in the day have to do it and submit our work?
So I am not gonna have, I decided I'm gonna have, I forgot to mention this. So the first quiz I'm gonna do next week. And yeah, it's gonna be through Canvas. I still gotta figure out how to implement the Canvas quizzes. So it was a bit, I haven't 100% figured that out. So there's no quiz this week. But I will talk more about that when I figure it out.
Okay, that's
But there
fine. I just wanted to check because I just knew that's how 250 did it, so I wasn't sure if that's what you were going to do or not.
Yeah, those are going to be done through Canvas. They'll be
Okay.
Canvas quizzes, and I'll send out emails. We'll talk about that when I figure that out completely.
Thank you.
Yeah. All right. Have a good one, guys.
Thank you.